Well, I would say thank you very much for inviting me to Pittsburgh, but I'm not there. And if you're very happy or if I say something funny, please be very quiet. And I'll know that you're actually cheering or applauding. All right. I am going to give you a talk about recent progress in measuring the expansion rate of the universe using parallax, Cepheids, type 1a supernovae. I'm sure the details will go by fairly quickly, so I have a couple of things that you could take a look at. On the lower left there's a review from this meeting from last year and our team's most recent paper. And I should say I'm going to be presenting work on behalf of the SH.ES team. Okay, oops, let me go on to my next slide there. All right, so after 100 years of research, we have arrived at a standard model of cosmology, what we call vanilla lambda CDM. It has 6 free parameters and a number of ansatz. It's dominated, of course, by dark sector components, dark matter and dark energy. Now, we don't really understand very well the nature of dark matter or dark energy, but we can take some naive guesses about them. In the case of dark matter, we assume it's a perfectly cold, collisionless particle. It's perfectly stable, no interactions. In the case of dark energy, let's assume it's a cosmological constant. With these assumptions, we can use the standard model as it would have looked shortly before recombination, which you see here over on the left. We can use that model to predict the physical size of fluctuations in the plasma shortly after the Big Bang. And then we can compare the size of those physical fluctuations, foremost being the sound horizon, but we also use the model to predict the baryon density. And we can compare those predictions to the observations of the angular spectrum of fluctuations in the cosmic microwave background. By making that comparison work, by varying the parameters, we essentially calibrate the 6 free parameters of the model, and we can also check some of the ansatz as well. And then we allow the model to evolve as the physics tells us it should. And so over time, the model starts looking more and more like the one you see here on the left as we get to the present time. And that allows us to predict the expansion history of the universe. So the universe expands since the Big Bang as following the model. Now we have what I would call guardrails along the way. We have observations of high redshift phenomenon like baryon acoustic oscillations and high redshift supernovae. They don't tell us that we have the right model, but they keep us from sort of going off some of the bends and curves in the expansion history. And finally, this whole process leads to a prediction today of how fast the universe should be expanding, what we call the Hubble constant, and that is 67.4 plus or minus 0.5. So this is incredibly precise, and so a very powerful end-to-end test of this whole story of the cosmological model, and in particular of these dark components and the assumptions that we make, is to try to measure the actual expansion rate of the universe, the Hubble constant today, to comparable precision. So a little more than a decade ago, my colleagues and I started a project, the SH.ES Project, in order to do just that. The idea was to build a strong and simple, what we call a distance ladder, starting with geometry, and that's done in multiple ways, to measure the distance to Cepheid variables. Cepheid variables are giant pulsating stars that can be seen in distant galaxies. They're 100,000 times as luminous as the sun, and the frequency with which they pulsate correlates very strongly with their luminosity, which makes them great standard candles. And then in some galaxies, we can see both Cepheids and type 1a supernovae. Those, the latter, are exploding white dwarf stars near the Chandrasekhar limit that explode and reach billions of solar luminosities. Now, we thought we could reduce uncertainties over the previous generation's attempts to measure the Hubble constant by particular ways in which we collect the data and by making observations in the near infrared. And I'll say more about that as I go on in this talk. And then finally, by thoroughly propagating the statistical and systematic errors, and particularly the covariance between error, we thought we'd get realistic errors to compare for this ultimate end-to-end test. So I'm going to walk you through this distance ladder now, and I just want to make a few general statements about distance ladders. Distance ladders in principle are simple and empirical. There's really no physics involved as long as measurements are obtained in a very consistent way. So in step or rung one, what we call the anchor step, we use geometry. You could think of this as, you know, running a tape measure out to these Cepheid variables. In practice, that can be done with parallax or other techniques that I'll talk about in a minute, and is usually done on kiloparsecs or megaparsec scales. And then in rung two, we look at galaxies that recently hosted type 1a supernovae and look for Cepheid variables in those galaxies. Now, a common misconception is that the velocity of those galaxies matters. In reality, it doesn't. The only thing we assume in this step is that the Cepheids and the supernovae are located in the same place. They're co-located at the same distance. And this is usually done in galaxies that are 10 to 40 megaparsecs away. And then in the third or final rung, once calibrated, the type 1a supernovae are out into the Hubble flow. And so their redshifts, usually out at a redshift of about 0.1, allow us to measure the Hubble expansion. So just a couple of things to point out here. In a distance ladder in general, there's very little, actually no astrophysical modeling. There's no general relativity, and there's no lambda CDM. These are empirical standard candles which are co-located and so are used to measure distances out to gigaparsecs, starting with geometry and with redshifts to measure the expansion rate of the universe. The one really important thing, and I can't emphasize this enough, is that the measurements and the objects themselves have to be consistent across the distance ladder, which is really crucial to not have systematic errors built in. All right, so I'm going to start out at the beginning. I'm just going to give you a little bit of an overview of how some of these measurements are made. So let's start with geometry. If you ever took or teach an Astro 101 course, you teach that parallax, trigonometric parallax, is the simplest way to measure distances in the universe. You watch a star move back and forth relative to more distant stars over the course of a year. And of course, that motion is due to the Earth's motion around the sun and our changing perspective. And if you know the astronomical unit, the distance between the Earth and the sun, then you have completed a triangle and you can measure the distance. The problem is stars are very far away. So that parallax angle that you're trying to measure, the change in the position of the star relative to distant ones, becomes very small. So I show here an illustration of the nearest star, Proxima Centauri, as seen over the course of a couple of years by the Hubble Space Telescope. And the motion you see is combined a proper or drifting motion with the parallax motion. And so any motion you see perpendicular to the drifting motion is purely due to parallax, is a measure of how far away the star is. The problem is that stars we're interested in are really much further away than Proxima Centauri. We're interested in measuring the distances to Cepheid variables, which are typically kiloparsecs away. And so that angle shrinks by factors of 1,000, becomes on the scale of really less than a milliarc second. And so it's a great challenge just to be able to measure that angle over the course of a year. Just to put a finer point on this, to measure the distance to a Cepheid variable at a distance in the Milky Way of about 3 kiloparsecs means that we're trying to centroid that star and measure its back and forth motion, when that motion itself will be about 1/100th of a single pixel on the Hubble Space Telescope. And so if you want to measure a motion that's 100th of a pixel, you need to measure much better than 100th of a pixel. You really need to be able to measure to, at least 1,000th of a pixel. And so we realized a few years ago a new technique for doing this, and that is to spatially scan the telescope, that is, move it in one direction while we're observing. And so we get many chances to compare the position of a star to the other stars in the field, and that improves the precision of the measurement because you beat down errors in the sampling. And so if you're confused what I'm talking about, here's a little animation. We literally move the telescope and the stars go flying by, and we get many samples of their position that we can compare across the image. And so here's a tiny patch here of one of those images, and you can see very well that you're getting a lot of information. And so that's really why you can improve upon this measurement over staring mode. And so then you go in and you extract scan line by scan line, star by star, those scans. And here is a number of those in a single image now lined up in time. When we first looked at this, we were pretty amazed to see that kind of noise you see in the direction perpendicular to the scan. But we quickly realized, oh, that is not noise, that's jitter. The telescope is bouncing in the direction perpendicular to the scan, but that's okay. That's called jitter. And when we compare the positions of two stars, we're essentially subtracting or removing that jitter. And so you get this nice smooth line you see at the bottom here. And by removing the jitter and then by averaging over thousands of pixels, we quickly found we could get to a precision of 20 to 40 micro arc seconds. So about an order of magnitude better than before. 1 second. All right, thank you. So moving on, over the course of about 4 years, we were able to watch this back and forth motion of about 8 of these very distant Cepheids in the Milky Way galaxy, which gave us a calibration that was good to about 3% for those Milky Way Cepheids. Meanwhile, there's a European mission called Gaia, which has been measuring parallaxes over the whole sky. And so we selected 50 other Cepheids whose flux we can measure with the Hubble Space Telescope, but whose parallaxes were measured by Gaia. That gave us another 3% calibration. And so over the last couple of years, the calibration, what we call the Milky Way period luminosity relation of Cepheids, shown here, has been much better determined now with 3 different techniques for measuring parallax. One using an old technique on Hubble, the fine guidance sensor, the spatial scanning technique that I described in blue, and the Gaia European space mission in purple. And these are all quite consistent. And they've also allowed us now to calibrate Cepheids with longer periods that are as long as what we see in the more distant galaxies, the supernova hosts. Now, if all goes well, if Gaia is able to reach its ultimate predicted capability in the next couple of years, this should be good to about a 0.4% calibration of the Hubble constant, which would be fantastic. Now, measuring parallaxes is not the only way to geometrically calibrate the luminosity of Cepheids. There are other ways. Parallax is maybe the most famous way and is maybe the gold standard, I guess I would say. But there are also using what's called detached eclipsing binaries. These are stars orbiting other stars, and with the Doppler effect, you can measure their radial velocities and the eclipses, and that gives you a physical distance that you can compare to an angular distance that's determined through interferometry and a relationship with the Planck law. That gives us a very precise geometric distance to the Large Magellanic Cloud. Or alternatively, observations of megamasers in the galaxy NGC 4258 observed in the radio over the last 15 years. We see these masers in Keplerian motion around the supermassive black hole, and that gives us a geometric distance. So all of these techniques have really come of age in just the last few years, giving us sub 2%, close to 1% individual geometric calibration of Cepheid variables. All right, let me move on to rung 2. Rung 2 is where we look at galaxies that recently hosted Type 1a supernovae, and then we use the Hubble Space Telescope to see Cepheid variables in those galaxies. This is really one of the main reasons the Hubble Space Telescope was built, and I would say it's maybe its chief superpower is to be able to resolve Cepheid variables in those galaxies. Now, this is also the rate limiting step for measuring the Hubble constant, because the precision goes as a single supernova, which is about 6%, over square root n, the number of these galaxies in range of observing Cepheid variables. And so in the last 35 years, there have been a total of 38 galaxies in this range. About 19 were measured in this way a few years ago by our team, and we are just now in the process of completing the other 19, the second half of the sample. I'll say more about that later, but that's one of the bigger improvements I think we can look forward to in this area just in the next year. Here are the Cepheid period luminosity relations in each of these host galaxies. So this is how we actually calibrate the supernovae, is to observe a bunch of Cepheids in each of these galaxies and map out its period luminosity relation to determine the distance to these galaxies. We do the same thing in the anchor galaxies, the first step, either the Milky Way or the Large Magellanic Cloud or NGC 4258, as shown on the bottom here. And this is one of the key aspects that has made these measurements more precise than a generation before, is the fact that we've used the same telescope, the Hubble Space Telescope, to observe all the Cepheids along the distance ladder in both the anchor galaxies and the supernova hosts. So past questions that used to plague measurements, like, what is the flux calibration of your telescope when you're using different telescopes, drops out of the problem because we're using the same telescope. People used to think we were crazy wanting to use the Hubble Space Telescope to observe, stars in our own Milky Way that are almost bright enough to see with your naked eye. But that's what you need to do if you're going to cancel the flux calibration errors. And so we've done that very carefully over the last few years. We have also improved measurements over the last decade by making our measurements in the near infrared, not just the optical. In the near infrared, most stars, including Cepheids, are better distance indicators simply because we can see through the dust in these galaxies. And also, there is less sensitivity to differences in the chemical abundances of the stars. This is well illustrated here in these period luminosity relationships for 70 Cepheids we observed last year with the Hubble Space Telescope in the Large Magellanic Cloud. And starting from the bottom, which is the optical, as you move up the sequence to redder and redder light, finally the near infrared or de-reddened near infrared, you could see the scatter become smaller and smaller because you're defeating the dust and chemical differences to get a very precise distance indicator. Each of these is good to about 3% in distance. The third step is the one that's probably was in the best footing to begin with. That's the Hubble diagram of Type 1a supernovae, just the objects that are used to measure the expansion rate of the universe. Now, you don't want to do this too nearby because otherwise there can be additional motions besides the expansion of the universe, what we call local flows, the fact that there are concentrations of matter drifting in different directions. And so we go above that. You don't want to go to too high a redshift because you don't want to become sensitive to changes in the expansion rate that arise naturally in cosmology. That is the acceleration of the universe, what the mass density of the universe does to change the expansion rate. And so there's kind of a sweet spot here in the middle where we have a few hundred Type 1a supernovae that are used to measure the intercept of the Hubble diagram. So then we do this all in one simultaneous fit. So the distance ladder really is a simultaneous system of equations. It's a multilinear regression that keeps track of the data, the covariance between a number of linear parameters and the data itself. What comes out at the end are just two numbers. One is the absolute luminosity of a Type 1a supernova, and the second here in red is the intercept of the Hubble diagram. Now, just to make this very clear what it is that we're doing, this is actually what the data looks like. So this is the distance ladder data again. So as I described before, step one is where you have 5 different sources of geometric calibration. So that's on the x-axis here, to calibrate the luminosity of Cepheid variables. So the Cepheid variables here are on the y-axis. Now, once they're calibrated, you essentially, in the second step, the Cepheids now show up on the x-axis because they're calibrated in the first step, and then they calibrate the newcomer here, which is the type 1a supernovae, on the y-axis. This is done now in 19 galaxies, but soon it will be 38 when we double the sample. And then once the type 1a supernovae are calibrated in the third step, they end up on the x-axis to calibrate redshift and tell you the Hubble constant, which now here is on the y-axis. So in the last few months, the most recent results from this route give you a Hubble constant of 73.5 plus or minus 1.4, so a total uncertainty of 1.9%. And if you have not developed amnesia since the beginning of the talk, you may remember that this is quite a bit higher than what we saw from the route measuring the early universe from Planck, and then using the cosmological model to predict the Hubble constant today. In fact, the tension right here alone from this measurement is 4.2 sigma, but I'll say more about other measurements in a second. Let me just, we'll zero in a little bit on some of the aspects of this measurement that you might be concerned about. So it used to be that the hardest part of the distance ladder was the geometric step, just geometrically calibrating, getting geometric distances that were good. And so this has become quite a bit stronger in the last few years. And so what I've done here is broken out the five different sources of geometric calibration that we use. Now we use all of them, but you could see individually, they all give values that are quite consistent for the Hubble constant, from about 72 to 76, consistent within about 2 sigma from each other, but they all have very independent systematics. And so this is, I think, a very powerful test of the first step, and demonstrates that you know, no matter which of these anchors you pick, it's very difficult to get out of this tension from a problem in the first run. Now, of course, the measurement itself and the tension can be described in one number, which is really the difference represented in the data. And that difference is about 20% or 0.2 magnitudes in the brightness of these really two kinds of standard candles. Looking at the data statistically, you can see that's very far off. Seeing an error that big would be represented by the red dashed line in the residual panel of either of these. But that, of course, doesn't address all kinds of other systematics. And so we took on about 23 different variants of our analysis, things that people had in the past suggested could be systematic uncertainties. And so here, this is showing those different variants. So we varied the reddening law, that is how the ratio of the dust to how much dimming it causes, though since we're observing in the near infrared, we don't have much effect there anyway. How we handle outliers, if there are Cepheid outliers, whether the period luminosity relation of Cepheids is treated as a single slope or multiple slopes, whether we allow for a chemical abundance gradient in each of the galaxies and regress that out, where we start the Hubble flow for supernovae, which light curve fitter or tool we use. Oh my gosh, I got to really move along here. All right. And so the errors have come down over time, as you see here, particularly improvements in the anchor steps most recently. I'm going to skip this here, but just to say briefly, I guess, that various methods that have used Cepheids and type 1a supernovae have given very consistent results over the last 20 years. However, other measurements now, other probes of the late universe have also given very consistent results. Cepheids, Miras, here's tip of the red giant branch, lensing, surface brightness fluctuations, and one-step methods, strong lensing and masers all by themselves in the Hubble flow, so that you can actually produce data combinations from these, eliminating any one thing that you're uncomfortable with, any peremptory challenge. And these are the different summaries that you get here. You can play the same game in the early universe. Here is Planck and the different CMB experiments, or ignoring CMB altogether, using baryon acoustic oscillations and Big Bang nucleosynthesis. And you can see that the tension is quite strong. In fact, here's a tension matrix. This is actually the difference in the Hubble constant. Let me move on to the tension matrix. And so you can compare any late or early measure of the universe. And if we kind of focus in here on Planck for a minute, you see that the tension ranges, depending on which of these tools you use, from about 4.5 to about 6.3 sigma. And so it's gotten quite serious, I would say. I'm going to skip this statement unless somebody asks during Q&A whether we can live in a void. The answer is no. I'll get close to ending here by saying that the reason for this we don't understand, and I don't feign a hypothesis, but people have suggested that various ways of changing the sound horizon in the early universe, particularly by injecting energy in the early universe that causes the universe to expand faster, becomes transparent earlier, shrinks the sound horizon, can change the early relative to late predictions. You know, people often ask me, can we believe these results if we don't know the reason why for this tension? And I think that is the history of science, is lots of times we see things we don't understand, and they sort of live with us as very important problems until we have an understanding of them. We're increasing our sample over the next year, as I mentioned. The error should come down considerably over the next year, hopefully to about 1.3%. And my final thoughts, since I only have a minute left, is so the discrepancy at this point is really about 5 sigma. It depends exactly which combination of tests or measures you use. It could be as low as 4 or as high as 6, but there's really no late universe measurement that is lower than any early universe measurement. It's robust because we can replace any single measurement and get the same results. So I think it would really require multiple catastrophic failures to avoid this. I think it's very interesting, I would say, unless your Bayesian prior on lambda CDM before this was much higher than 5 sigma, because that is really the level of the significance. I don't know what's going on. I don't know why this is. It looks like a very robust signal, as I said, independent of any one single measure. So I think we have to keep following the evidence. And we just may have to admit that the universe is smarter than we are now. So I'll end there with take any questions that you have.
Thank you very much, Adam. That was a very interesting talk. We have time for questions, which I don't see anything yet, but you know, okay, there is one question that just came in from Manuel Buenabad. Could you remind us why we cannot live in a void?
Yes, I can. Let me just back up a little bit to that slide. So the reason, here's my slide on voids. So we could live in a little void. We could live in a void that would change the Hubble constant. You know, you would expect by maybe 0.5% or so. And that's been determined by doing 2 different things. One is sort of theoretical. You take our description of large scale structure in the universe and you do a large n-body simulation and you vary our position in that box. And when you do that, you can turn that into an uncertainty in the Hubble constant, a variation that you expect, and it's about 0.5%. Or you could determine this empirically by going out further and further with type 1a supernovae and looking at the size of fluctuations that you see in the expansion rate, and that's also 0.5%. So 0.5% is reasonable. However, in order to get out of this problem, you would need a void that is about 9% in the Hubble constant. So that would be about 15 to 20 sigma in terms of living in a special place in the universe. If you were at all off center of such a void, it would create a giant dipole in the cosmic microwave background, which we don't see. And so, yeah, you can vary the Hubble constant at 0.5% or even 1%, but you can't get out of this problem because we would have to live right in the center of an enormous 15 to 20 sigma void.
Thank you very much. I'm trying to see if there are Any more open questions? I don't see any open questions, but Adam, I think
I may
we
ask a
also have,
question. I cannot submit it to the Q&A because I'm an organizer, but if I'm allowed to ask, this is Iris.
okay, please go ahead.
I would be curious if you could say something about whether there's any prospect to fill in data between the early universe and late universe measurements of the Hubble constant.
Right, that's a great question. So there is data in some regions. So between about redshift 0.1 and 2, there is baryon acoustic oscillation and high redshift supernova data. The problem is that data doesn't carry its own absolute scale. And so this is really a scale problem we're seeing between the late and early universe. That data is happy to get calibrated at either end. And in that way, I described it at the beginning of the talk, it's sort of like guardrails. It tells us that the changes in the expansion history of the universe predicted by lambda CDM seem okay, but they don't tell us, you know, this is more like building a bridge across a river at both ends. You know, you start on one shore, you start in the other, you end up in the middle, and you haven't met. And you know, you can't blame some of the bricks along the way. They were perfectly straight bricks. It seems like, you know, the scale, the places you started with on opposite shores seem misaligned, and you know, a few more bricks in the middle don't seem to help us very much.
Okay.
Thank you.
I'm trying to see if any new questions have come in so far. I don't see anything, but since you have, Adam, since you have about like 1 or 2 minutes left of your time, if there was anything that you would have liked to emphasize that you think went over too quickly, please take a minute.
Yes, one thing that I wished I emphasized, oh yes, this. Yeah, I just wanted to emphasize that, as I said, the reason that we think this is robust is these represent different data combinations in the late universe, where you could get rid of Cepheids, you could get rid of tip of the red giant branch or Miras. These are all different techniques. You could get rid of the use of the Large Magellanic Cloud, the Milky Way, NGC 4258, lensing, no supernovae at all, and in all cases you're ending up with something around 72 to, you know, 74. And, you know, playing the same game in the early universe, you know, you could do away with Planck and, you know, you're still in the same place. You could do away with the CMB, but, you know, you're still using the early universe because you're using a Big Bang nucleosynthesis to calibrate baryon acoustic oscillations. So if people get confused, what do I mean by early or late? If your measure depends on knowing the number of neutrinos in the universe, for instance, then that's an early universe measurement. If it has nothing to do with neutrinos, you know, it's a late universe measurement. And so, you know, this is really a statement of something different, apparently, in the way we see the early universe and calibrate things in the early universe, when the cosmological model looks so different, is dominated by things like neutrinos and radiation, and the late universe, where it's dominated by very different things.